Okay, now we're going to switch. The measuring tools you will have for the balance of the class today. So you can go over on your own. And once again, if you don't find it comfortable, please let me know, and I'll work with you. We will not go to the other lab because it's Good Friday, because we need to spend some time going over that. What time is it? What is it? Okay, you got it. Okay. There's that micrometer here later on, okay, that you can find, as well as vernier calipers, micrometers, and I strongly suggest, okay, take your time, because next class meeting again, I'll give you a quiz, hands-on, the test, okay, for measuring tools, and it's a very important part of the grade. It's not going to be the whole thing, but it's very, very important. Okay. Now let's go back and review some of the things. If I may have your attention back there, later on we're going to discuss the measuring tools. The one thing, as I mentioned before several times, every drawing today that appears in industry will have some designation as to what standard that drawing was made. If you do not have designation to what standard, then everything is kind of wishy-washy. Basically, everything is possible. Everyone can interpret his or her own way. Okay. So when you see that that's for ANSI, ASME Y 14.5, 1994, that strictly means 1994 is the governing document that the measuring and tolerance of the drawing, okay, we have to comply with. Okay, simple as that. Even though since 1994 we had several revisions, but when I manufacture per 1994 and you inspect per 1994, the customer has to buy by that standard. He cannot demand to have a newer standard or older standard. It just wouldn't work. Likewise, when it comes to your test, whether we find on the drawing to have just the basic dimensions like I have given here, or dimensions that would be also with these symbols, makes no difference. We still have to conform to this standard here. American National Standard Institute or American Society of Mechanical Engineering. The Y14.5 is the, excuse me, a committee for dimensioning and tolerance. There are zillions committees there, as you can imagine, with every possible standard that we have in our books. Okay. So, for example, we have just a very basic print here with the basic size, 1 inch plus minus 10, with no additional information, meaning geometric configuration requirements. We still have to conform to that standard, which simply means if you, as a mechanical inspector, inspect the first part and you find it's 1 inch and 10,000, would we accept this part or not? Yeah, we would accept on that size. Why? Because it does meet the tolerance. That's upper limit, right? It's a high limit. Okay, but how much out of straightness can this be? The out of straightness, okay, is going to be 0. Out of straightness is going to be 0. Why? By rule number 1. Remember? Everyone understand that, right? So we have a chance today to go and clarify once again how that works. Next class meeting, you will not have that chance. So if there is any doubt whatsoever that you don't understand why it would be 0 out of straightness, this is the time to ask, right? So even though we did not have feature control frame underneath it, that size, it's still under rule number 1 under this given standard, means when it is 1 inch and 10,000, which means under maximum material condition, it has to be tolerance has to be preserved, which means cannot be out of straightness by any. Okay? Yes, Chuck, question?
Oh, scratching my head.
Yes.
Sorry.
All right, back there. Are we clear with that?
Yes.
Everyone? All right. Therefore, if the next pin when you check out turns out to be 1 inch and 9,000, what will be allowed out of straightness with that pin? A shear. Oh, a shear is not here.
0.001,
What is it?
100,000, or
Whoa,
1.001.
100,000? Okay, well, that will be 0.001 is correct. But that will be 1,000 over there. 1,000, not 100,000. Yeah, you have to watch for the terminology as well. So we would be allowed to go then to 1,000. Okay, 1,000 over there. What about if it comes down to be 1 inch and 8,000? How much out of straightness can that be? Okay. The gentleman just walked in. We'll give him the honor for answering that question.
You want to repeat the question?
Right. If the pin was measured 1 inch and 8,000, how much out of straightness can it be based on? And by the way, I realize just walked in and probably have no clue what's going on. Which is okay, just have a chair and take a look at it. We have a basic pin with respect to dimension, with the given tolerance zone, and she is the inspector. And when she measured the second, or rather the third one, the pin turns out to be 1 inch and 8,000. This pin does not have any of these requirements. Can this pin be out of straightness at this size?
Yeah.
Okay, the answer is yes, I agree. But how much?
2,000?
By 2,000. Perfect. Why? Just tell me why and you'll make an old man happy.
Since it's not in this maximum material condition, it's a lot better.
Correct. As it deviates from the maximum material condition, which it did by 2,000, by the same departure from the maximum material condition, we gain the tolerance. Okay? So by 2,000. Okay, the second from the back. Okay? This dimension here, 1 inch and 5,000. Would we accept that or not? Based on that size. It's 1 inch 5,000. Would we accept this or not? Yeah, we do. The size conforms to what? The limits, right? Okay. How much out of straightness, if anything, would it be allowed? Pardon me?
You said radiance? Radiance?
No, out of straightness. Can this pin be bent? And by how much if that is the case?
Yes, it can be.
Pardon me?
It can be.
It can be bent. Okay, by how much? He just defined it. He just gave us definition just a second ago. If that was 5,000 below the maximum material condition,
Yeah, 5.
it can be bent up to 5,000. It cannot be bent more, but it can be bent up to 5,000. Okay? So what we have here is naturally, then that will be 5,000. Okay, now we're making some progress, seemingly. Okay. What happens if with 1 inch and 1,000? Good or bad? What do you think? One inch and 1,000? Would we accept? Okay, we would accept the size. Why? Because again, it falls within the range. Right? So we have, how much out of straightness can it be?
1,000.
Pardon me? 9,000? Okay. Well, okay, why 9,000? Here we have 1 inch and 1. Okay, 1 to 10 is 9,000, right? Okay, so we have, okay, for 1 to 10, so it would be 9,000. And 1 inch, And what about if we have 990,000? Chuck?
That's acceptable, and you have 20,000, it can be out of straightness.
Out of state. Okay. So 990,000, we will accept size, and that will be out of state by 20,000. Now that means in exaggerated sense, okay, between this point and that point, it could be up to 20,000. Now, if that is the case, and all of this is correct, the question is how that would function. If it's 990,000 and 20,000 hours straightness, is it going to fit somewhere? Okay, let's take the extreme. If that's 990,000, in main part, we have a bushing that's going to go through that. What will be that minimum size of bushing? Based on that criteria that we just defined.
1 inch and 10 thousandths.
1 inch and 10,000. Okay. Why? It could be, but why?
Because
I'm asking for a minimum size of the bushing. You see,
Right.
if we didn't go through the final product here, if we didn't go and define each one of these materials, you have that pin and disregard what they may turn out. What would be the mating size, absolute minimum size of that bushing?
I'm sorry, say that one more time.
Okay. If we didn't have already pins as to produce, to be measured, if you just have a drawing, you have 1 inch plus minus 10,000, and your boss said, okay, well, figure out the mating size, meaning the bushing, what would be absolute minimum size? Well, obviously, we have to meet the largest possible size, right, if the pin is made, to 1 inch and 10,000, okay? So if that is the case, then we would have 1 inch and 10,000, that would be the basic size of that bushing. Therefore, would that bushing have to be straight then? Perfectly cylindrical? Or could it deviate in any way? Well, the question leads to the logic of what would be the tolerance? Would it be plus or minus? That would determine which side is the maximum chill condition, right? Right now, we'll just determine if the pin is made of 1 inch and 10,000, it has to be perfectly cylindrical, right? Therefore, the bushing made of 1 inch and 10,000 has to be perfectly cylindrical. If that happens to be the at maximum chill condition, right? Therefore, that has to be what? The minimum size. Does it make sense? It has to be absolute the minimum size. Therefore, we could go plus something minus nothing, right? You can go below 1 inch and 10,000 because if your pin is producing 1 inch and 10,000, it's going to go. Okay. Therefore, if the bushing is produced at 1 inch 10,000, it also has to be perfectly cylindrical or straight. The axis has to be straight. Therefore, you're going to have a sliding fit in a way, right? How much more sliding depends on surface texture, meaning the texture and so forth. Okay, how much tolerance would you allow? Well, it becomes the question of functionality. It will become the question as to what temperature these parts would operate under. Is it going to be in a boil room, okay, with elevated temperature? Therefore, what kind of material? Is it made out of aluminum with a higher coefficient of expansion, right? Or is it made out of steel, cast iron, bronze, brass, or whatnot? All of the factors, okay, you have to obviously consider. But right now, if we were just to say plus 3,000, okay? That means I will have bushing minus nothing plus 3,000. Okay, And therefore, how much of a clearance would we have with this extreme position? That we have a 990,000 pin size. It could be out of straightness by 20,000. Would it still go through that bush?
Yes.
Yeah, it would go to the bushing, because you still have 3,000 clearance, right? So even though it's bent like heck, all right, but it's going to go through it because you still have a, even if we did not have 3,000, would it go through that?
Yes.
It would go through that. It was made just 1 inch and 10,000. That can be the way it is, okay, as bent, as an exaggerated sense. It would still go through that because, or as long as we do not violate rule number 1 per ANSI 114.5 standard, we're sure. See how critical it is for you as engineers to really get this once and for all and hang on to this? Because that's going to be part of your, career for on and on and on. Okay? Okay. So that's us, all right? Now, what happens that the pins are still the same size, but we have this attached onto the sides, below the sides, or above this makes no difference how we package. Then at 1 inch and 10,000, how much out of straightness are we allowed based on this? What do you think? Yeah. How much out of straightness? You said 3,000 straightness. First of all, what is the straightness symbols apply to? Does it apply to the surface, the part of geometry, or applies to the diameter, the metrical? Pardon?
The diameter?
No, it applies to the surface, to the form, not to the metrical axis. It's not an axis. Okay. So, if we have this, and we still have a pin of 1 inch and 10,000, how much out of straightness are we allowed? What do you think?
Probably be the same.
I mean,
The same. Same as
yeah, if we have a pin that's 1 inch and 10,000, and we have that feature control frame says straightness up to 3,000, how much out of straightness would that pin be allowed at 1 inch and 10,000? Pardon? By 1,000. Okay, it will not be allowed at all. Why? Because rule number 1. Rule number 1 states, when the feature is made at its maximum material condition, which is 1 inch and 10,000 maximum material condition, right? It cannot violate the perfect envelope form. In other words, it cannot be out of straightness, but nothing. Okay, period. Okay? So therefore, even at 1 inch and 10,000, we still would have a 0 tolerance, or 0 out of straightness. Okay? It's a very important principle to remember, because from that, everything else is covered. This controls the form, not the axis of that part. It controls the form. How do we know that? Well, there is nothing in the feature control frame other than straightness and 3,000. 3,000 simply means up to 3,000. Right? Okay. Tell me, at 1 inch and 9, will we produce 1 inch and 9? How much out of straightness is allowed? This being underneath of that, next to me is 1 inch and 9,000. Pardon?
100,000.
Pardon?
1,000.
1,000. Okay, you're correct. Has to be 1,000. Why? Because it departed from the maximum material condition by 1,000. Okay? All right? The next one, what do you think? I want each and 8. You're correct. What? It departed from maximum kill condition by 2,000, right? Okay, so we have 2,000. Okay? Nothing changed. Now, at 1 inch and 5,000, what do you think? Pardon me? 3,000. Perfect. Why 3,000? That is the maximum. That is the limit. Okay, and that goes, okay, how much do we have out of straightness by 990,000 that it turns out to be?
3,000.
Pardon me?
3,000.
3,000. Why? Because that doesn't change. It's 3,000. Okay? You see the beauty of that? It limits us. It says, if it's a maximum drill condition, it's a 0 out of tolerance. It cannot be out of statement. But when it departs, by the same departure, okay, we can go up to 3,000. It departed by 1,000, okay, here's 1,000 out of statements. Departed by 2,000 up to 2,000. Okay, when it came down to, it went to 5,000 below, whoops, 3,000. That is the maximum out of statements allowed. Okay? Please, keep that in your mind. This is your last chance to really, really clarify that. Okay? Okay, then we move on to this here. Okay, assume now that you have this feature control frame under the basic dimension with respect to tolerance. At 1 inch and 10,000, okay, right back. What do you think? At 1 inch and 10,000, how much out of straightness is it allowed? Pardon me? Pardon me?
Oh, I haven't said anything yet.
Well, please do, say something.
1.003.
Okay, that's something that's going to really get you a bad mark on the test. You've got to speak the shot language. I would agree 1.003. I would agree with that. But if you write it down, okay, like that, that's a minus. So it's a sharp terminology, which we have discussed, okay? Yes, it will be 3,000. 3,000 of an inch. Why? Because that's what is stated there, okay? So what you're saying is, at this 1 inch and 10,000, it will be 3,000. Now just tell me why would it be allowed to go up to 3,000? Because if you were to tell me, you would tell me because of this symbol here. That controls the axis, not the form. That is the center of that pin that goes through that. You and I don't see it, but it's there. As we turn this around 360 degrees, that axial relationship is right there. So it could be 3,000. And since there is no modifier next to that, like we have here, that would mean the entire range of the dimensions, as long as dimensions are to be accepted as a valid, it would be 3,000. That means regardless the feature size, right?
Can you explain that a little more?
Yeah. When we have a feature control frame with the diametrical tolerance zone, the rule number 1 does not apply, which simply means this. By rule number 1, when it controls the form, meaning surface, when that feature, meaning pin, when it's produced at the maximum allowed size, which means it's a maximum trill condition, the outer straightness is not allowed. It has to assume so-called perfect envelope form. It has to be perfectly cylindrical.
Because of the center axis?
No. We're talking about two different things right now. When you don't have that diametrical symbol in the feature control frame, that means it controls the form, it controls the surface. When you have a diametrical symbol in the feature control frame, such as we have it right there, that controls the axis. What's the difference between the two? The axis, we will have to turn the pin 360 degrees. As we turn 360 degrees, what we actually are doing, we're turning around its axis, right? When it comes without a metrical symbol in the feature control, we're controlling the surface, just across that surface, without turning, okay? So if I put down on the surface table, right, and I go like this, and I check, that's it. With the axis, when I turn, 360 is going to plump, 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 right, if it's out of straightness. That is the difference. So the rule number 1 applies to the form control, not the axis control. That's a big difference. Okay? Okay. Now, we have the next one. The same, it's an axis control, right? 3,000, but there is a modifier. It says it controls it's to be 3,000 under certain condition. And that certain condition would be when the part is made, as the symbol implies, at its maximum material condition. Okay? So in this particular case, the maximum material condition would be again 1 inch in 10,000, right? So we would have 3,000. Okay. As we depart from the maximum material condition, we go from 1 inch in 10 to 1 inch in 9. We depart by 1,000, right? We have a bonus there by 1,000. So we have a 3 plus 1 is going to be 4,000, right? That symbol enables us to gain bonus tolerance, which is, in practical sense, cheaper to produce, cheaper to verify, and definitely more likely to fit whatever the mating part we're going to have. Now, when it comes to 1 inch and 8,000, we depart by 2,000, so it's going to be 5, and go down all the way down to 20, base to 990, and 20,000, okay, there, plus 3, that would be 23,000. Okay? Is this clear? Okay, that modifier is very powerful. That simply says, this is specified, you cannot do anything without. This is it. 3,000 from the maximum material condition to the least material condition. But the modifier says only if it's at maximum material condition 3,000, as it departs from the maximum material condition, we're going to gain additional bonus tolerance to the same departure value as it departed from the maximum material condition. Simple as that. Okay? Now the question is, with this here, what will be the mating size part? Okay, here.
Say that again?
Given this stipulation, okay, that we have this feature control frame under the given dimension, and you need to figure out what would be the bushing mating part, what would be that minimum size. How do you go? You know, I mean, think about it. Now, if you remember the virtual condition formula, which states the virtual condition, okay, for outside dimension is when size is a maximum material condition plus the geometric tolerance. Now that makes kind of at least leads us into the right direction, right? Okay, based on that formula now, what will be the absolute minimum size of that bushing? What's the maximum material condition of a pin? 1 inch and 10,000. What is the tolerance given? What? 3,000, right? So we have 3,000. So the basic size is going to be therefore 1 inch and 13, right? That is the base, that is the smallest size bushing that we can have, okay? Now we have to add or subtract something, right? But in this particular case, do we add the tolerance or do we subtract the tolerance? We cannot subtract because that will be the minimum opening of that bushing dam. Therefore, it has to be plus. So we're going to have a plus. And once again, let's say 3,000 and minus nothing. Okay. What does this mean? Well, that means as the pin decreases in size, from the maximum material condition to the least material condition, is going to be more bent, right? But it still is not going to violate the perfect envelope form based on this formula here. Because with size of maximum material condition plus geometric tolerance, we're going to have a 1 inch and 13,000. And even if we didn't have anything, but we have to have, because of manufacturability, right? We have to be able to produce that bushing, okay? So we're going to have a plus 3,000 minus nothing. And the pin, even with 20,000 being out of straightness, okay, and 23,000 is still going to go through that. You see the beauty of the GD&T? It controls the form, controls the axis, basically controls the form, okay, through the axis, and adds the bonus tolerance to the size, which is much cheaper to produce rather than to be rigidly held onto the basic dimension or just plus minus 10,000. Okay? That's what I've been trying to impress you the whole semester, to basically buy into that logic, okay? Because it's a kind of a form term or principle because we don't use it in everyday communication. But needless to say, it's there for you as mechanical engineers. It's always going to be there. And there's no way around it. Now, as I mentioned, in the old days, we still use to some degree. We had a fitness. We had so many different categories of fitness, slide fit, force fit, interference fit, and whatnot. And it's being used today, but for the most part, okay, we find the GD&T, okay, does stand out over and above everything else. Because everything is based on the maximum material condition and the rule number 1 when it comes to the form control.
My question is,
Yes.
can you explain, like, how does it work as far as material in the virtual condition formula? Like, how is it different from those two?
The virtual condition formula is used when we need to determine the mating size, okay, the mating part size. Like, we're always going to have 2 parts to mate somehow, right? So if you produce the pin first, and as an engineer you ask also to design a part that pin's going to go through that, right? It is going to have a mile-long kind of a clearance, plop, 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 okay? But it's going to be kind of a close fit, but nevertheless it's going to go without interference. Then you take the size of your pin, what its maximum size allowed per your design, and then you add the geometric tolerance which you're going to have at that maximum material condition, which we have 3,000. So we have when it's sized at its maximum material condition plus the geometric tolerance. That gives you the minimum size of the mating part. That's how we got to be, the basic size of that bushing is 1 inch and 13,000, and we added 3,000 clearance. That is debatable whether you want to have a 3,000 more or less. But we know we cannot go below 1 inch and 13,000. Now, the other side of the formula is, if I had a bushing first design, if my bushing is 1 inch and 13,000 plus 3 minus nothing, I would take that virtual condition formula in reverse order, which would be, that's funny, which would be at maximum material condition size minus the geometric tolerance. Therefore, maximum material condition would be what? 1 inch and 13,000, right? Minus 3,000, that would be 1 inch and 10,000. So my largest pin size would be 1 inch and 10,000. See, it perfectly fits. That's why we would add geometric tolerance when we are figuring out the mating part for the outside dimension, and we would subtract geometric tolerance when we're figuring out the mating size for inside dimension. Simple as that. It does take, again, this particular principle does not come from everyday's usage, verbiage, and whatnot. It's a very specific, you know, you have to talk about nuts and bolts business. And we don't talk behind the dinner table, okay, about nuts and bolts business usually, right? Unless you sit behind my table then, you know. Okay? Any questions? So on your test, I'll assure you, I will not go beyond this. I will go with the similar problems. Because if anything I can hope for at the end of this semester is for you to take this with you, and that would be the ultimate benefit of this lab experience that you have this semester. And once again, not only to remember it for my beautiful eyes, but to remember it for something that's going to be far more lasting and important in your career as a mechanical engineer. Any questions? No questions? Going once? Going twice? Going 3 times? Yes?
For this scenario that we have here with the modifier, when you do the universal conditions for the outside diameter for the rest of those dimensions, actual sizes, are you going to change the plus or minus tolerance, or is that going to remain the same because that's what's given you?
They're basically still the same because that's a clearance. In either case, we are looking for clearance. How much clearance we're going to have. Therefore, the only clearance would be the positive, the plus side, right? If we go to minus side, then we would not violate. We would violate then, okay, the very principle we're talking about. So that's easy. And how much we want to have a clearance will depend on many factors again. If you have aluminum coefficient of expansion is much faster than a steel, what kind of steel and whatnot, then you want to have a more clearance. If I have a 4140 steel, which is relatively slow coefficient of expansion, then I'm going to have a less of a clearance. Again, is it going to be an agriculture piece of equipment installed, or is it going to be in a jumbo jet installed? There are all kinds of factors you're going to have to go through that. But just as a matter of basic principles, yeah, the clearance always comes with plus. Like if you have, when we say sliding fit, that when you have 2 parts that are going to fit into each other, just sliding without any clearance. Well, actually, we will have clearance, otherwise they wouldn't go, right? You may have a 2/10 of clearance. But if you don't have a clearance, then you have what? Interference, like in a force fit, when you have to use a hammer, okay, to force something, yeah. That could be the minus side. Okay. Anything else? Again, I'm very much open for the balance of the day to go over that. Obviously, the measuring tools are here, and we're going to go through that. And we'll, oh gosh, it's almost 10:30. So what I would suggest is you're going to have that. You're going to have 14 symbols, straightness, flatness, blah, 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 down the line. Okay, you have to recognize. You're still a little bit of my concern, the terminology. This 0.003 has to be spelled out phonetically. It's a 3,000 of an inch, or the 2/10 of an inch, or 1,000, and so forth and so forth. Okay? Because that's the only way that you'll be able to sail, okay, through on the job interview and beyond. Once you're on the job, then it's going to come and become second nature as far as that goes. Okay? Any questions?
No.
okay?
Let's do some more.
What I would suggest is, pardon me?
Let's do some more.
You want to go with that? Okay, right. Let's take, if I may, Council, let's take 5 minutes break and then we'll come back and continue. Thank you.